Okay, so let us see about quantum algorithms. Actually, all of us know an algorithm is a set of instructions used to perform some well-defined task on a computer. Now, a large part is to develop a quantum computer has come from the discovery that some algorithms work dramatically better on a quantum computer or a quantum system. Usually, what happens is the same classical algorithm that has been extended or made capable to work on a quantum system is what our motive is in studying quantum algorithms. Okay, now what exactly is the benefit of a quantum algorithm is that a quantum algorithm is capable of evaluating the function at multiple values of x simultaneously. Okay, how I will justify this is, suppose if I talk about a qubit which exists in superposition state, the ket xi, alpha ket 0 plus beta ket 1. It exists in a superposition state, giving a quantum computer a hidden realm where exponential computations are possible here. Okay, in other words, the quantum system can exist in superposition or linear combination of states. This helps us to do simultaneous parallel operations. Simultaneous parallel operations. That means what? Actually, we have discussed in my introductory in my introductory videos that usually it is all about getting, when I toss a coin, it's all about getting a head or a tail. But instead, quantum helps to find at that point of time what is the state of that coin. Means it is in that flipping condition only, it is in that flipping state only. At certain point of time I would like to know what's its status, so it helps me to find out the status at any particular point of time. That's the benefit. Okay, so it allows to do simultaneous parallel computation that cannot be done even in principle on a classical computer. Okay, now talking about quantum algorithms, first thing that we should remember are of course, there are a set of quantum algorithms, the Deutsch algorithm. Okay, the Deutsch and Joza algorithm, the Deutsch algorithm, the Deutsch and the Joza algorithm. Okay, the Shor's algorithm and the Grover's algorithm. These are the major ones. If any new algorithms are found out, it definitely would contribute to a new research area in quantum. Okay, as of now, these are the algorithms that are there. Now, before learning any of these algorithms, there are some basic things which I should be aware of. What that is first thing is the Hadamard gate that is being used extensively. Hadamard gate that has been used extensively in some of the quantum algorithms. All of us know what is Hadamard gate. I know the matrix for the Hadamard gate. This is the matrix. Now, coming to what happens if it is applied on the computational basis, guys. These are the qubits, guys. Basis. These are called basis. Different names, the qubits, basic qubits, these are called, also called computational basis, because they form the basis for the quantum computing. Usually they are called with these names. Anything else, if I remember, I'll let you know, but then this is it. Now I can write the operation of Hadamard gate on ket 0, or the basis computational basis ket 0, to be like this. Of course, you can observe it by applying matrix multiplication, guys. Ket 0 minus ket 1 by root 2. Ket 0 minus ket 1 by root 2. Now, what's it about the Hadamard gate that I need to know? Let me talk about Suppose I have applied it on ket 0, I have applied it on ket 1. What if it is applied on ket xi? Let us see. H ket xi, if I apply on it, what happens? What is ket xi? It is alpha ket 0 plus beta ket 1, right? So alpha is a constant, it can be taken out. Beta is also a constant, it can be taken out, and H is applied on those basic states. Now alpha, I know what's the value of it. Ket 0 plus ket 1 by root 2 plus beta ket 0 minus ket 1 by root 2. Okay. Yeah. Of course, you can separate the coefficients of ket 0 and ket 1, guys. What are the coefficients of ket 0? Alpha plus beta by root 2 is the coefficient of ket 0. Alpha minus beta by root 2 is the coefficient of ket 1. Okay. Of course, this feature has another name in quantum. It is called quantum interference. Quantum interference. What this says is, suppose if I actually there was only alpha as a quotient for ket 0 and beta as a quotient for ket 1. But then what has happened is, for the ket 0, the coefficient or the probability has changed from alpha to alpha plus beta by root 2. For the probability for ket 1 is changed from beta to alpha minus beta by root 2. This would be called quantum interference, and usually you observe this quantum interference with Hadamard gate. Okay. Yeah, this is one point which I will tell. I will do separate video on quantum interference talking about it in detail. Now here what I want to stress upon is applying Hadamard gate twice. Applying Hadamard gate once again. I will say here once again. Of course, it is twice, second time. It is second time. What happens is H of alpha plus beta by root 2 ket 0 plus alpha minus beta by root 2 ket 1. This is equal to, of course, alpha plus beta by root 2 is a constant, so H ket 0 plus alpha minus beta by root 2 H ket 1. Okay, of course, I know those values as I have written in the beginning only. So what happens? Alpha plus beta by root 2, this value H ket 0 is nothing but 0 ket 1 by root 2 plus alpha minus beta by root 2 ket 0 minus ket 1 by root 2. Okay, just try to simplify. Again, again collecting the coefficients of ket 0, what do you get? And collecting the coefficients of ket 1, what do you get? See, collecting the coefficients of ket 0, I'll be getting alpha plus beta in the first term and alpha minus beta in the second term. Of course, divided by 2, because root 2 into root 2 becomes 1, right? For ket 1, it would be what? Alpha plus beta, again plus alpha. Oh, there is a minus sign here. So it would be minus alpha plus beta by 2. Okay. So what happens? Just see here. Beta and beta gets cancelled. Alpha and alpha gets cancelled. I'll be left with 2 alpha by 2 ket 0 plus 2 beta by 2 ket 1. Okay, this gives me what? Alpha ket 0 plus beta ket 1, which is nothing but the xi that I have considered. Okay, I will rewrite this again, guys. Just see here. Applying H gate twice. Okay, rewrite it as a circuit. Just see. There is a ket xi. I have passed it through Hadamard gate once. Again, I have passed it through Hadamard gate again. Okay, I get back my Ketzai. Okay, or in other words, this can be called h squared is equal to identity, or h squared Ketzai, this is equal to Ketzai. Okay. Yeah. So what I can say, if two Hadamard gates are applied in series, this is in series, guys. All of you know parallel means like this, series means like this. Okay. So if two Hadamard gates are applied in series, then I on a ket, then I'll get back its original state. Get back its original state. This is one point that you ought to know before proceeding with quantum algorithms. Of course, suppose what happens if I apply what if H is applied in series, H is applied, I'm sorry, in series is over, applied in parallel. Parallel means how? There's a Ketzai, H is there, okay, and there is a Ketzai, another H is there. If they are applied in parallel, what's the output? Okay, let us see. Okay, when I'm talking about a circuit in parallel, there's an important point to be noted here. When I'm talking about a circuit in parallel implies tensor product. Tensor product. Here again, I will write the same thing. What that is a circuit in series. A circuit in series implies matrix multiplication. Matrix multiplication. Okay, this you should be clear. That's why I've written with the different color. Okay, of course, let us see what happens if I'm connecting in the place of xi, if I'm putting 1. If I am applying H gate in parallel, okay, something like H on ket 1 and ket 1. This gives me what? I know how tensor product of operators works. One for one. One operator for one qubit, another operator for another qubit. Okay, very simple, very obvious. H1 I know ket 0 minus ket 1 by root 2 is 1. Ket 0 minus ket 1 by root 2 is another. Okay, so what do I get? Tensor product, of course, 1 by root 2, 1 by root 2 becomes 1 by 2, guys. So tensor product of 0, 0, tensor product of 0, 1 with a negative sign, tensor product of 1, 0 with a negative sign, and tensor product of 1, 1 with a positive sign. This is how it works when the circuits are in parallel. In series, I'm sorry, in series. Okay. Of course, you can do the same thing for, I can do the same tensor product kind of thing for these also. What will they be? H ket 0 and H ket 0. Okay, these are ket 0 plus ket 1 by root 2 and ket 0 plus ket 1 by root 2. Similar statement like the above one I will get, but with all positive signs. 1 by 2, ket 0, 0, ket 0, 1, ket 1, 0, and ket 1, 1 as what I will get. Of course, guys, you might think why ma'am is writing repeatedly like this. There is a shorthand notation for it. That is, this is how I will write. I can write, this is how. This is a shorthand notation. Usually you come across. Suppose if I have 3 guys, H tensor product, H tensor product, H tensor product. Of course, I should have 3 qubits when 3 gates are being operated. That is obvious. This can be written in shorthand notation like this. Okay. Of course, here also I can write like this, guys. Okay. That also is allowed. Now, generalization of it, let me talk about generalization of it. Of course, here also let me write here. Tensor product, get 0, tensor product. Twice. Okay. Any doubts? You feel free to post under the video. I can clear that. Okay. Now, generalization. Let me talk about the generalized version. Generalization of tensor product. I will say of tensor product. I will write the statement. Just see here. Suppose if I have tensor product of n copies of ket 0. Okay, then what I will do is, it is like h. Of course, if I have n copies, then I have to apply n. Okay, and then this with ket 0 n times, then this can be written as h tensor product of n ket 0 tensor product n. This is how I will write, guys. Of course, for the 2 1, I also have a notation. Just see here. I also have a notation for 0 1 1 1 kind of things. Okay, shorthand notation we will call it. What that is I have done for 0 0 and 1 1 na? Let me do it for h tensor product of 0 and 1. Okay, if I do this, then I'll be getting something like 1 by 2. All of you are aware, right? Minus 0 1 1 0. I think I have done it above. I will just scroll it so that I have done this above. This is for both the zeros. The above one is for 1 0 and 1. Okay, for 1 I have done. 1 1 I have done. Okay, it is not for 0 1. Right. Now this is it. And what happens? Suppose if I take x to be, x is assumed to be running over the numbers, 0, 1, 2, no, running over the numbers, these numbers I will talk and assign them 0, 1, 2, 3. Over the numbers 0, 0, 0, 1, 1, 0, 1, 1. That is 0, 0 is 0 and this is 1. I suppose this is 2, this is 3. Then I can write this tensor product in another notation also. That is 1 by 2 is common, of course. Summation x belongs to 0, 1. How many times I applied? Twice now. So I can just say power 2 as well. Of course, first let me write this. Minus 1 power x, get x. Okay, if x is 0, then it is 0, 0. If x is 1, then it is 0, 1. Kind. Okay. Also, this one, there is another notation for this one. Which one? 1, 1, 1. Yeah, for this one, there is also a shorthand notation that I can write 1 by 2 summation x belongs to 0 comma 1 whole squared. Means it is I am in 2 qubit space. This means 2 qubits space. Okay, so I know the combinations in 2 qubits. I can rewrite this as x naught XOR x1 x. Of course, here also there should be square. That means what? I am in 2 qubit space, not in single qubit space. If it is on single qubit space, then it is just power 1. Okay, yeah. Now let us check one example, guys. It's a famous example. applying Hadamard gate. Okay, and with that I will just stop this video. Find the result. Find the result when Hadamard gate is applied to ket xi is equal to ket 0 plus minus 1 power x ket 1 by root 2. Okay, let's see what happens with this and then just end this video. Solution. H ket xi, this is equal to alpha h ket 0 will come. Minus 1 per x is a constant. So beta, no, there is no beta, right? There is a beta. Alpha is not there. Okay. Okay, just a second. If I am applying on a generalized ket, then I will talk about that and then come to it. Okay, generalized ket and qubit using superposition would be what? And I will compare both of them. I think that should be easy. Now, generalized ket in this is ket xi is equal to alpha ket 0 plus beta ket 1, right? So, alpha h ket 0 plus beta h ket 1. I know these values as in the beginning of the video we made a mention of them. Right? So, alpha plus beta by root 2. This is all about quantum interference, again, which I made a mention in the beginning of the video. Okay, after this, what I will do? I will apply now h ket xi, I mean on the given ket. Okay, so what happens here? The result would be h ket 0 and h ket 1 would give me what? 1 plus minus 1 power x by 2 ket 0 plus 1 minus 1 power x by 2 ket 1. How it is? Just see guys, just see. In the place of alpha, I have 1. In the place of beta, I have minus 1. Here I have 1. I have minus 1 power x. So, it's alpha plus beta and alpha minus beta. So, accordingly, I have taken, instead of going with the typical difficult or typical part. Okay, so obviously this is root 2 and this is root 2, right? Yeah. So, okay, there was there is already a root 2 with it, and now ket xi also, given ket xi also has root 2, so it becomes 2 only, right? This is it. This is how it happens. Now, let x is equal to 0, then h ket xi would be what? If x is equal to 0, what happens to h ket xi? My anything power 0 is 1 here and here. So this term goes to 0 and I will be left with the h of ket 0 plus ket 1 by root 2. This would be what? Ket 0. Now, if x is equal to 1, these are the only possibilities, right? H of ket 0 minus ket 1 by root 2 will be there. This would be nothing but ket 1. You can just check guys how it turned out. When x is equal to 0, what happens? It is nothing but 2 by 2, right? 2 by 2, so it is 1. So ket 0 plus, of course, indirectly in ket xi, what is ket xi? 0 plus minus 1 power x by ket 1 by root 2. In this you can substitute x is equal to 0. So x is equal to 0 gives me ket 0 plus ket 1 by root 2. Okay, x is equal to 1 gives me ket 0 minus ket 1 by root 2. Hence the result. This is how things will happen. Okay. Now it's all about Hadamard gate, of course, in quantum algorithms, what is the point that I wanted to stress in this video or focus on this video is, what if the circuit is in parallel? How do I take things? What if the circuit is in series? Also, guys, when the circuit is in parallel, there is one thing. Since I have applied H gate only twice in parallel, there is no problem. In series here, I have applied H gate only, right? So there was no problem. But there is one more thing that I need to tell you, that when if I am applying one H gate, one Z gate, another some phase shift gate or something if I am applying, then how will I write? The notation is PZH Ketzai. Okay, what it is it is ulta. It is ulta of this. I don't take directly, but here what happened was, in this case both are H only. So if I show it a ulta also, it may not be clearly visible because both are H. But then when a series is when a circuit is in series, then it is all about matrix multiplication, as I have made a mention. Along with matrix multiplication, the format in which the matrices should be written is in ulta of the circuit, ulta order, reverse order of the circuit. Okay. Yeah. With this, I will just stop this video. Thank you for your patient listening.